Hello, everyone. My name is Evan Dewald. I'm a grad student at Carnegie Mellon, and today I'll be presenting my work on a private ledger architecture tailored for secure workflow management in additive manufacturing facilities. This work was supported by my advisor, Dr. Jack Buth. Especially in the past year, I've gotten more interested in the data management side of AM and the infrastructure related to it. If you have any questions or comments about this presentation, feel free to reach out. I want to start with my upfront conclusions. First and foremost, I want to recognize and convince you that this AM digital thread that we're so familiar with has vulnerabilities, especially at the transition points and these different interfaces. We'll talk about what those attack vectors look like and how they take shape. What many have suggested and proposed is that a blockchain-based solution is a promising potential solution to this problem. But I want to recognize that the conventional platforms, everyone has a preconception of what they think of as a blockchain. And these conventional platforms are often not well suited for AM or any really industrial supply chains. We're going to deconstruct a blockchain to its most basic components and then rebuild it and tailor it to our use case to make sure it meets the speed and cost requirements that we need. We're going to embed this blockchain as a backend to a custom workflow management application that you may be able to implement in your AM lab. I'll show a demo of how that works. We have a modular smart contract that accepts arbitrary file types, allows you to set role-by-role permissions, and it's completely customizable to your needs. It also implements a lightweight custom consensus protocol, and we'll discuss how that works. So I want to start by unraveling this AM digital thread. You guys have probably seen slides like this. The basic concept of the digital thread is that, of course, we have our physical component, our feedstock, our fabricated part that undergoes post-processing, heat treatment, and disposal. But along the way, we have a digital twin that takes the form of these different file types, whether that's CAD files, build preparation, characterization, and test data. And the idea here is that by the end of a life cycle of a given component, it may have been touched both physically and digitally by perhaps dozens of different entities. And I want to focus on these different transition points, these interfaces between, for instance, the design stage and the build stage, because these state changes represent a vulnerability to our digital thread, where it could potentially either be purely stolen. IP theft is a big problem in AM and in a lot of manufacturing fields, not only of your design files, but also your proprietary build recipes and even test data. A more malicious potential attack vector is where if somebody knows what they're doing, they could intercept this file, this CAD file or this build recipe, and embed a micro defect that's undetectable by human eye, but eventually results in catastrophic failure. So in the same way that we can apply one of these tamper evident tags to perhaps our powder lot to make sure that it hasn't been tampered with between when it left the manufacturing facility and reached us, we need one of these tamper evident tags for our data flow. And so one of the potential solutions to that is coming from the world of cryptography. And to simplify how we're going to use this, we're going to make use of something called hashing algorithms. These are essentially what they call one-way functions. And what this means is that it's very computationally simple to go from an arbitrary input to a fixed length output, but it's probabilistically impossible to work back the other way. You're essentially left with a brute force method of trying to reverse engineer the input from the output. These hashing algorithms have some key benefits that will work in these applications that we're focused on. So first and foremost, being sabotage detection. So if we think about this case where a small micro defect is embedded in our STL file, it might be very difficult for a human operator to tell if something's been changed in that file. But the way these hashing algorithms work is they take advantage of a property called the avalanche effect, where even if you change a single byte in this input file, perhaps embedding that small defect, it results in a drastically different output. So you see these random combinations of letters and numbers. That's our hash, that's our output. And so by simply computing the hash before and after each of these state changes, we can tell whether it's been tampered with along the way. Another inherent benefit is arbitrary file compression. So as we know, in AM, we're dealing with a variety of different file types and file sizes. We have build images, parameter sets, Excel spreadsheets, billing data, all these different files. It doesn't make sense to tabulate them, the files themselves, in something like a spreadsheet or a database. So we can represent these files by simply tabulating their hash in the database. And this will allow us to represent even very large files in something more in a fixed length output, for instance, 256 bytes. And so we're going to build on these hashing principles as the foundation for a special type of data structure, an append-only database. And so I want to consider this data structure as a single block of data. And this block is going to contain some header information, some perhaps timestamps and public keys of the different actors involved. But the most important part is these transactions. And I want to think of the transactions as these proposed state changes, for instance, updating your CAD file, proposing post-processing and heat treatment. And what we're going to do is take the hash of this entire block and link it in the header information of block n+1. And as we start to link these blocks together, the effect is we have an append-only and also immutable ledger, because if I were to alter anything in block n, it immediately invalidates all the blocks forward if you were to start computing these hashes. So in our digital thread, it makes it clear that something's been tampered with at some point. Now, of course, this data structure alone is somewhat meaningless. We need a way also to establish agreement about the current state of the ledger of the digital thread. And we do that through something called a consensus protocol. Now, this is where we get into the parts of the blockchain that you're probably most familiar with. The consensus protocol, the most famous consensus protocol, is called proof of work. And this is where you have that specialized hardware, those graphics cards churning up a lot of energy and taking a lot of time to compute these highly intensive calculations to ensure that it's exponentially more difficult and prohibitively expensive for a malicious actor to try to change a block that's already been mined. Another one is called proof of stake, where essentially somebody who wants the privilege of validating blocks has to put up a large sum of initial capital, and they lock that away. And if one of these validators are to act maliciously, they give up that huge sum of money. So essentially, these two ingredients, the specialized data structure and the consensus protocol, and the consensus protocol can vary. These are the ingredients for a blockchain. So we've kind of deconstructed it to its most basic components. And now we're going to start to spin it up to suit our needs for an AM supply chain. So as opposed to something like proof of work, where we have this specialized hardware, high costs on the Ethereum network, which is kind of the state of the art, most famous in terms of a problem like this, it's as much as $20 per transaction, because you have to compensate these miners for expending all these computational resources to add your new transaction to the ledger. So I want to move to something more lightweight, more efficient, with real time and virtually no cost. And what I'm going to discuss here is something called proof of reputation, a different type of consensus protocol that's more suited to a private network, like what you would experience in your AM facility or in your lab. So I want to start with that assumption that this is a private network, not a public network like Ethereum or Bitcoin, where anyone can act anonymously and they don't necessarily have to trust the validator nodes for doing their work. So think of your organization-wide intranet, and we're going to start to build the different actors that would participate in this type of ledger. So we, of course, have our engineering teams and our students. These might be the people making those updates to those CAD files and submitting those build reports, also the billing information, the technicians. And we also have more privileged parties involved here. And those can be the project managers, think of your principal investigators. And these actors will behave as the validators in this private network. So their identities, this is a critical difference from a public blockchain where everyone is anonymous. These validators, their identities are public to everyone in this working in this network. And how this scheme is going to work is simply participants are going to send their unconfirmed transactions to the validators, who are going to sign off and add the block to the ledger using their public private key signature. So every one of these blocks, you can see exactly who validated it and who is responsible for it. And if we think about first of all, this is a very computationally efficient process. There's no specialized hardware. It's a simple process to actually sign these blocks, and the validators don't have to do anything unless they're trying to behave maliciously and trying to alter this ledger. We think about the incentive structure here. Because the validators' identities are public, it's in their best interests to not try to manipulate things. It's easily auditable because of that chain-like structure, either by these participants or the other validators. It's clear if something was altered and exactly by whom. And this keeps our incentive structure in place, allows us to perform real-time validations in mining without all these other costs associated with some of these public ledgers. I also want to introduce this multi-layered permissioning structure that I'm going to implement in this custom ledger. And the main idea here first is that obviously on a private network, even on a private network, not all transactions should be fully visible to all participants. So if you think of Alice and Bob are working on updating this CAD file, doesn't necessarily make sense that Joe, who's in another group in another lab, also has access to that sensitive information, those sensitive documents. So what we're going to do is, since only the parties who are actively engaged on that contract are going to have access to the files themselves, we're going to do that by encrypting these files to simply only be accessed by Alice and Bob. But we still need some sort of information to be represented on the blockchain, and that'll simply be the hash of these files that we talked about earlier. So what I want to also address is that these files themselves, we're not replacing your standardized file storage, whether that's AWS3, you use Dropbox or Google Drive. This solution is not a replacement for that. So you'll still store your files on your preferred storage format. In this case, in this demo, I'm going a more decentralized route and using something called the interplanetary file store, but it all works the same way. So think of when you post something on Dropbox, you get a shareable link, and that link represents the file in a much more compressed way. So this is kind of a little trick of how we can represent these large files on something like a database without weighing it down. And so you'll encrypt the file to just Alice and Bob, upload that to your preferred file storage, and that spits out a URL or an addressable key that is what's actually stored on the blockchain. So this allows us to represent all this data and keep the blockchain running with all the key cryptographic benefits without any of these security concerns. So the smart contract is the rules of the road for interacting with this ledger. And so I'm stealing this term from the the world of Ethereum, but it essentially works the same way in this custom ledger framework. So the demo that I'm going to introduce uses these steps of submitting a build. This might be an STL file, selecting a powder lot, submitting a build report, a PDF file, or something of that nature, submitting post-processing, and then an invoice. And I want to just touch on some of the key properties and benefits of the smart contract as I have it constructed here. So first is modularity. You can obviously adjust the order in which these take place, add different steps. So if you want to start including process monitoring data or test data, you can easily do that and have these happen asynchronously or in some sort of procedural manner. Of course, we're also accepting a variety of different file types. And a unique property here is that this allows you to apply role-based permissions. So when I was thinking about how my lab works, there's certain jobs that the technician is responsible for and certain jobs that the engineer or the student is responsible for. So usually the engineers are the ones updating the CAD files and the technicians handle the billing, but both might have a hand in something like parameter planning. And so I want to make sure that our smart contract reflects this inherent nature of our AM lab and how these different roles interact. And so I have a demo here. Hopefully that's visible. So again, the user interface leaves something to be desired. That's a point of future improvements, but the basic functionality and the back end is what we want to focus on. So this is our workflow management application for our AM supply chain. And I've created a dummy account that's just an admin role. That'll allow me simply to move a little bit more quickly through this demo. So we open up our homepage and I can see two panes here. First of all, the projects that me as the admin role are interacting with, and also some recently mined blocks. This is how we'll see when we go through this demo, how things are being added to this immutable ledger. So again, a key point here is these are only the contracts that me as the admin at cmu.edu role are interacting with. They're not what other participants are using. So I'm going to show quickly how to make a new project. We'll call this TMS test project. I'm going to assign a technician. And so I've created another dummy account that's just technician at cmu.edu. I just have to find a file. Think of this as an STL file that I'm uploading here. And just to show what other types of data we can store in this, this is just think of a JSON document or a Python dictionary that's storing all this data, but it's all going to be securely encrypted. So we can handle test comments or Oracle string if you're thinking about billing. So I submit this transaction. It's been proposed to the ledger, and now we see contract 19 is now visible in our My Projects pane. See our timestamp, and you see that it's at the contract submitted current state. We also see a new mined block show up here. We can see our transaction hash and the hash of the previous block. And that's how we will validate this ledger moving forward. And so when I open up an individual project pane, I can really start to visualize my digital thread in this way. And so I am currently in the contract submitted state, but we'll see as I work through these panes. So as I discussed earlier with the role-based permissioning structure, normally only a technician I assigned the roles of being able to select powder, but just in the interest of time, the admin account has kind of all-encompassing permissions. So I'll say we're using 316 lot 1. Now we see, okay, in our digital thread, we see that powder ID show up. And we saw a new mined block because of that new transaction happen in real time. And our contract 19 here, is now in the powder selected stage. So similarly, I can work through this entire digital thread, submit a build report, PDF, do post-processing and invoicing. I think you get the general idea, and it'll start to propagate this project state. And of course, this project information is only visible to me as a participant engaged in this contract. If I were to double click, you see the file is downloaded and decrypted successfully. So if somebody else in my network or a malicious actor coming in, if they were to try to download one of these files, they would have no luck opening it because it's still encrypted. So I hope this quick demo shows you how this works overall. And just to revisit these conclusions, have this toy demo in a GitHub repository if you're interested, but it's definitely not a commercial application yet. I hope we touched on some of these points and why a blockchain makes sense, but only if it's able to meet our real-time needs and low-cost requirements. And this workflow management application can be customized to your use case or the conventions that you use in your lab. It can be as open or as closed as you wish. So thank you. Go ahead and stop the recording. Feel free to reach out if you have any questions.